are the fraction of molecules versus kinetic energy for gases at two different temperatures. Which statement is true? Where'd my pen go? There we go. So again, this is a graph. This is what's called a Boltzmann distribution. Boltz, B-O-L-T-Z. Boltzmann distribution of the kinetic energies and fraction of molecules. Well, for us, a couple things to point out about this. The fraction of molecules always has to add up to 1. And one of the results of that is the area under curve A and the area under curve B. Those areas must be equal. So those areas are equal because, and that's a result of the fact that the fractions add up to 1. And all that's happening as you go to higher speeds or higher temperatures using the relationship that the average kinetic energy is proportional to temperature is that as temperature increases, average kinetic energy increases, and these curves get squished to higher kinetic energies. So if we look down here and we're trying to answer this question, it says, so we know that A is for a gas at lower temperature because A is a curve at lower kinetic energies. And line A is for a gas at lower temperature than line B. That is true. So that is the answer for this one. For this one in particular, I think there's only one question, so I think I just told you the answer, but I did, even though the pool is only one question deep on this, although there may be a couple variations, but for now I think there's only one. This is an important concept, and there's a couple things that we want you to be able to do. So we want you to understand that at both curve A and B, some gas molecules are going very slowly because they have very little kinetic energy, and some are moving very quickly. They have lots of kinetic energy. There is a distribution of kinetic energies. That's where that term comes from. And if I were to ask you to draw the average kinetic energy, the average, because there's such a high fraction at the lower kinetic energies, the average is right about there on the curve for curve A. So I'm going to write KE average for curve A. And again, you don't have to draw it precisely. It's somewhere past the big hump and somewhere here for average kinetic energy for curve B. Okay, and again, those don't help you answer the question, but what you can see is with this relationship, average kinetic energy is proportional to T. Since the average kinetic energy is larger, for curve B, that means it must be at a higher temperature. Are there any questions about this? Okay. The one last thing I'll mention is that often these curves don't have any numbers on the axes, and we think of this as more of a qualitative understanding than a quantitative understanding with numbers, and that's fine. That's what we're going for.